Hello everyone, welcome to the lecture again. In the last two classes, we discussed about the simple harmonic oscillator, for example, a spring mass system without any damping. But in real systems, the damping are always present. Therefore, let us discuss the damped harmonic oscillator. Okay. So, the equation of motion is F equal to m a. So, m x double dot equal to the forces. So, there will be the spring force minus k x minus let us say a velocity dependent damping. So, let us say some gamma x dot. Okay. Here this gamma is the damping coefficient. Okay. So, this is the simplest type of damping, for example drag, because it depends only on the velocity, and this gamma x dot is basically the damping force. Okay. Let us call this as equation number 1. Now, to solve this equation, let us define as earlier omega equal to square root k by m and let us say some zeta equal to gamma over 2 m omega. Okay. In that case, I can write down equation number 1 as x double dot plus 2 zeta omega x dot plus omega square x is equal to 0. Here this zeta is the damping ratio. Okay. Now, let me call this as equation number 2, and this is the differential equation of a damped harmonic oscillator. Okay. Now, equation number 2 can be solved mathematically, and its general solution is x equal to a1 e to the power lambda 1 t plus a2 e to the power lambda 2 t if lambda 1 and lambda 2 are different. Okay. Here this lambda is the solution of the characteristic equation lambda square plus 2 zeta omega lambda plus omega square equal to 0, and this equation we get by replacing d2 over dt square by lambda square and d over dt by lambda in equation number 2. Okay. So, we have to solve this equation to find out what are the lambdas. Okay. Its solution will be lambda 1 equal to omega minus zeta plus square root zeta square minus 1, and lambda 2 will be omega minus zeta minus square root zeta square minus 1. Okay. So, therefore, x will be a1 e to the power lambda 1 t, lambda 1 is minus zeta plus square root zeta square minus 1 omega t plus a2 e to the power minus zeta minus square root zeta square minus 1 omega t. Okay. Let me call this equation number 3. So, this solution we wrote when lambda 1 and lambda 2 are distinct, that is they are different. If lambda 1 and lambda 2 are same, in that case the general solution is x equal to a1 plus a2 t e to the power lambda or lambda 1 t. Okay. Now, this quantity zeta, okay, can be more than 1, it can be smaller than 1, or it can be 1. Therefore, zeta square minus 1 may be positive, negative, or 0. Okay. Let me write down equation number 3 once again. We had x equal to a1 e to the power minus zeta plus square root zeta square minus 1 omega t plus a2 e to the power minus zeta minus square root zeta square minus 1 omega t. Okay. Now, let us look at the case when zeta is more than 1. This is called the overdamped system. Okay. In this case, the roots lambda 1 and lambda 2, that is this one and that one, they are distinct, they are different, and they are real and they are negative. Okay. Therefore, equation number 3 suggests that the solution or the value of the x is going to decay exponentially. Okay. So, therefore, equation number 3, it decays and there is no oscillation, okay, or there is no periodic motion. Okay. So, let me just plot for some representative value of xi, equation number 3. So, let us say this is t axis and this one is x. So, in this case, this is the plot of x. So, let us say this is for xi equal to more than 1, let us say 2.5, and of course, this is overdamped system. Okay. Now, let us look at the second case when xi is equal to 1. This is called the condition for critical damping. Critically damped. System. So, in this case, the roots lambda 1 and lambda 2, they are equal, they are real and they are negative. Therefore, its solution will be x equal to a1 plus a2 t e to the power minus omega t. So, again it is an exponentially decaying function. So, the motion decays and again there is no oscillation. Okay. So, let me again plot it. Okay. So, this is the case when zeta is equal to 1, this is called critically damped system. Okay. Now, let us look at the case when zeta is smaller than 1, that is called the underdamped system. Okay. So, in this case, because zeta is smaller than 1, therefore, zeta square minus 1 will be negative and therefore, its square root is going to be imaginary. Therefore, lambda 1 and lambda 2, they become complex. Okay. So, here as I said, zeta square minus 1 is negative, therefore, roots are complex. In this case, x1 will be a1 e to the power minus zeta plus I square root 1 minus zeta square omega t plus a2 e to the power minus zeta minus I square root 1 minus zeta square into omega t. Okay. And this equation I can rewrite as a1 e to the power I square root 1 minus zeta square to omega t plus a2 e to the power minus I square root 1 minus zeta square omega t, and then the common factor e to the power minus zeta omega t. Okay. Now, the quantity inside the bracket is in the form of e to the power I omega t or e to the power minus I omega t, which is an oscillating term, and the quantity outside the bracket is in the form of e to the power minus omega t, which is an decaying term. Therefore, this time the x is going to decay exponentially and simultaneously it is going to oscillate. So, the solution will look like this. So, this is t axis, this one is x. Okay. It will oscillate and it will decay. Okay. Now, this same solution I can rewrite in different form. So, the x can also be written as c sine omega square root 1 minus zeta square t plus phi into e to the power minus zeta omega t. Okay. So, this quantity that you see here is the same as this quantity. Okay. Now, let us define omega d equal to omega square root 1 minus zeta square. Then the above solution can be written as x equal to c sine omega d t plus phi into e to the power minus zeta omega t. Okay. And note that what is zeta? Zeta is defined as gamma over 2m omega, the damping ratio. So, zeta was gamma over 2m omega and our omega was square root k by m. Okay. Okay. So, just let me write down x is the displacement of the mass from its equilibrium position. Omega d is the damped natural frequency. Zeta is the damping ratio. Gamma is the damping coefficient. And k is of course the spring constant. Now, let us look at couple of problems based on these concept. The first problem statement is following. The 8 kg body is moved 0.2 meter to the right of the equilibrium position. and released from rest at time t equal to 0. Determine its displacement at time t equal to 2 second and it is given that the viscous damping coefficient is 20 Newton second per meter and the spring stiffness K is 32 Newton per meter. Okay. So, here this is the equilibrium position and it is given that m is equal to 8 kg and at initial time t equal to 0 the body is released from rest. So, therefore, x dot will be 0 and it is moved by 0.2 meter. So, x is equal to 0.2 meter and x dot is equal to 0. In the question we have been asked to find out at t equal to 2 second what is x, okay, and it is given that damping coefficient is 20. So, gamma is equal to 20 and k is equal to 32. Okay. We know that the x, which is the displacement of the mass from its equilibrium position, is x equal to c sin omega d t plus phi into e to the power minus zeta omega t, where this omega d is omega square root 1 minus zeta square and omega d is the damped natural frequency and zeta is gamma over 2 m omega, where this gamma is the damping coefficient and of course, omega is equal to k divided by m. Okay. So, let us first calculate the omega. So, omega is equal to square root k by m, k is given, m is also given. So, 32 divided by 8 equal to 2 radian per second. Now, let us find out zeta. Zeta is gamma over 2 m omega, gamma is given, m is also given and omega we have calculated, it is 2. So, therefore, that comes out to be 0.625. Okay. Since zeta is less than 1, therefore, the system is underdamped. Okay. And omega d which is the damped natural frequency, that will be omega square root 1 minus zeta square, and that will be 2 into square root 1 minus 0.625 square, that will be equal to 1.561 radian per second. Okay. Now, let us look at x. X will be c sin omega dt plus phi into e to the power minus zeta omega t. Let us put the values. So, that will be c sin omega d is 1.561 into t plus phi into e to the power zeta into omega. Zeta is 0.625, omega is 2. So, if you multiply, you get 1.25. So, e to the power minus 1.25 into t. This is the position at time t. Let us look at the velocity x dot. X dot will be the derivative of this. So, let us differentiate equation number 1 with respect to t. So, we get, so let us say this is the first function and this one is the second function. So, we get first function as it is c sin 1.561 t plus 5, and then the derivative of second function. So, e to the power x is e to the power x. So, minus 1.25 into t, and then differentiation of that will be minus 1.25, okay, plus second function as it is e to the power minus 1.25 t into the derivative of the first function. So, which is c cos 1.561 t plus 5, and then the derivative of that, which is 1.561. Okay. So, let me call this equation number 2. Now, initial conditions are given. Okay. So, initial condition, so it is at t equal to 0, x is 0.2 meter. So, let me put this in equation number 1. At t equal to 0, so we will have c sin phi equal to 0.2. Let me call this equation number A. Now, let us use the another condition. At t equal to 0, it is given that x dot is equal to 0. Therefore, we will have minus 1.25 c sin phi plus 1.561 c cos phi equal to 0. Let me call this equation number B. Now, there are two equations A and B, and there are two unknown c and phi. So, from A and B they can be find out, and it comes out that c equal to 0.256 meter and phi is equal to 0.896 radian. Okay. Let us put this value of c and phi to find out how x varies as a function of t. So, x comes out to be 0.256 e to the power minus 1.25 t into sin 1.561 t plus 0.896 meter. Okay. And we have been asked to find out x at time t equal to 2 second. So, let us put t equal to 2 second, then x comes out to be minus 0.0161 meter. Okay. Now, let us look at another problem, and the problem statement is following. The block of mass m is at rest in equilibrium position at x equal to 0. The system is underdamped with the damping factor being zeta equal to 0.25 if the initial condition on the motion of the block are x equal to 0 and x dot equal to 4 meter per second. Determine the displacement of the block at time t equal to 0.1 second, and it is given that use m equal to 0.2 kg, K1 equal to 20 Newton per meter and K2 equal to 30 Newton per meter. Okay. So, let me again write down that x is given by c sin omega dt plus phi into e to the power minus zeta omega t. Omega d is omega square root 1 minus zeta square. Zeta is gamma over 2 m omega and omega is square root k by m. Okay. So, here m is equal to 0.2 kg, zeta is 0.25 and the initial conditions are at time t equal to 0, x is 0 and x dot is 4 meter per second. Okay. And again we have been asked at t equal to 0.1 second what is x. Okay. So, previously we have one spring, in this problem we have two springs and they are connected in parallel. Okay. So, we know that when the springs are connected in parallel, then the spring constant k will be k1 plus k2. Okay. K will be k1 plus k2. Now, k1 is 20 and k2 is 30. So, therefore, k will be 50 Newton per meter. Now, let us find out omega. Omega will be square root k divided by m. So, for the combined system it will be square root 50 divided by m is 0.2. So, this comes out to be 15.811 radian per second. Okay. Now, zeta is given, zeta is 0.25. So, which is gamma over 2 m omega and it is given that it is 0.25. So, therefore, it is obvious that the system will be underdamped. Now, let us find out omega d. Omega d will be omega square root 1 minus zeta square. So, omega is 15.811 into square root 1 minus 0.25 square and that comes out to be 15.309 radian per second. Okay. Now, x will be c sin omega dt plus phi into e to the power minus zeta omega t. Let us put the values. X equal to c sin omega d is 15.309 t plus phi into e to the power minus 3.953 into t. Okay. So, let us call this as equation number 1. Now, x dot also I can find out by differentiating it. So, x dot will be minus 3.953 c sin 15.309 t plus phi plus e to the power minus 3.953 t into c cos 15.309 t plus phi into 15.309. Okay. Let us say this is equation number 2. Now, the initial conditions are given. Okay. And what are the initial condition? At t equal to 0, x is equal to 0. So, let us put t equal to 0 and x equal to 0 in equation number 1. So, we have c sin phi equal to 0. Let me call this equation number A, and at t equal to 0, x dot is equal to 4. Let us put that in equation number 2. So, we have minus 3.953 c sin phi plus 15.309 c into cos phi equal to 4. Let us call this equation number B. Now, again in A and B there are two equations and there are two unknown. So, that can be found out. So, from A and B you get C equal to 0.2613 meter and phi equal to 0. So, let us put this value in equation number 1 to find out how x varies as a function of t. So, let us put in equation number 1. So, you get x equal to 0.2613 sin 15.309 t and phi is 0. So, therefore, multiplied by e to the power minus 3.953 t meter. Okay. And we have been asked to find out x at t equal to 0.1 second. So, let us put t equal to 0.1 second. So, you get x equal to 0.1758 meter. So, with this let me stop here. See you in the next class. Thank you.